Let's look at some more examples involving areas and definite integrals. Problem number 14 in the book asks you to find a definite integral that represents this area shaded at right. It's the area underneath the graph of f of x equals 6 minus 3x here in the first quadrant between 0 and 2. Well, this isn't bad at all. Remember that the format is to put the function here and then dx, and write the endpoints of the interval along the x-axis here. So 6 minus 3x is the function, and we're going from 0 to 3 along the x-axis. Now you're going to have some other problems in the book which are going to ask you to find the area, but do it using geometry rather than using Riemann sums. So of course we could form a partition and do Riemann sums, but notice here, since I'm working with a triangle, I know that the area is going to be 1/2 the base times height. The base, of course, is 2. And to find the height, I need to know what this highest point on the triangle is, and that happens when x equals 0. And if I plug 0 into x here, I get a y coordinate of 6, which I've indicated in the picture. So the height is 6, and 1/2 times 2 times 6 is 6. So here we wrote a formula, and we also found what the area was geometrically. Here's another example where you're asked to use geometry rather than Riemann sums to find an integral. Let's say that it's the integral from 0 to 2 of the square root of 4 minus x squared. So here the function we're trying to find the area underneath is the square root of 4 minus x squared, and the interval we're working on is from 0 to 2. And they want us to use geometry. So what we need to do is graph this function and then try to recognize the area that we're looking for as a familiar geometric shape. So in graphing this, we might think of this as being y equals the square root of 4 minus x squared. So if you square both sides, that's y squared equals 4 minus x squared, or x squared plus y squared equals 4. Well, x squared plus y squared equals 4 is the equation for a circle. Is a circle of radius 2, centered at the origin. Now, if I work my way backwards, I have y squared equals 4 minus x squared. If I were to take square roots, I'd actually get a plus or minus square root. So since we're working only with the positive square root, the graph of this function is actually only the top half of this circle. Further, since I'm only going between 0 and 2, I only want the part of the circle which is on the interval between 0 and 2. So I can take this part away as well. So if I were to shade the region whose area I'm looking for, it would be this quarter circle in the first quadrant. So the value of this integral is the area of that quarter circle. So it'll be 1/4 pi r squared. And the radius of the circle is 2. So this is 1/4 pi times 2 squared, which is pi. And it's kind of cool that we can find this integral using geometry, because this is actually a fairly difficult integral to do using other techniques. In fact, it won't be until about a month into Calculus 2 that you'll learn how to carry out this integral using other techniques. But notice that using geometry is fairly simple. Now here's another property that definite integrals have. Or sorry, that Riemann sums and definite integrals have. Suppose that you're working with Riemann sums, but the function that you've got is negative. If the function's negative, then the graph looks something like this. It's down here rather than above the x-axis. Well, if you go through all the steps of finding the definite integral of f of x, then you actually do calculate the area of this region, but it comes out to equal a negative number. So the absolute value of this is the area of that region, but anytime you calculate a definite integral of a negative function, it gives you a negative area. So you should think about that. Think of areas underneath the x-axis as representing negative areas, so that when you integrate over with a function that's sometimes above and sometimes below the x-axis, then partially the areas might cancel out. And here's an example of that. Let's find the integral from 0 to 5 of 2x minus 4 using geometry. So let's see if we can draw a picture. The function we're working with is 2x minus 4, and the interval is from 0 to 5. Now y equals 2x minus 4 is a line. It's a line that has slope 2 and y-intercept negative 4. So if I were to graph it, it would look something like this. The y-intercept is at negative 4 and it has slope 2. So let's graph it between 0 and 5. Then when I carry out the integral, it's going to find the area of this shaded region, but the region down here is going to count as negative area, and the region over here is going to count as positive area. Now, since each of the regions is a triangle, we're going to be able to use geometry to figure out what each area is equal to. Now, we need to know what the x-intercept is. To find the x-intercept, we can set the function equal to 0, which gives us 2x equals 4, so x equals 2. So now, let's calculate the area of each triangle separately. For this triangle, the area is 1/2 times the base times the height. The base is 2, and the height is 4. And 1/2 times 2 times 4 is 4. But we're going to count this as negative. So with this first one, we're getting an area of negative 4. Now, one way we could interpret that, I suppose, is notice that this height is actually negative 4. So it kind of makes sense to have negative 4 as the height. Now over here, calculating area, the base is 3. And I don't see the height directly, so in order to find out the height, I need the y-coordinate of this point, which I can get by plugging 5 into the function. So notice that f of 5 is equal to 10 minus 4, or 6. So the height of that rectangle is 6. So the base is 3, and the height is 6. And 18 over 2 is 9. Since that region's above the x-axis, I'm going to count that as a positive area of 9. So the definite integral will be a negative 4 plus 9, or 5.